Here we are given that ABCD is a parallelogram and that angle A is a right angle. And our goal is to explain why angle B, angle C, and angle D have to also be right angles. Well, we know in a parallelogram that opposite angles are congruent to each other. So I'm going to fill that in. We also know that a property of parallelograms is that consecutive angles are supplementary. That means they add to 180 degrees. Angle D and angle C are consecutive angles in this parallelogram. So that means they need to add to 180 degrees. If this one's already 90 degrees, then this one has no choice but to also be 90 degrees to make the 180 degrees. And now we know that since this is a parallelogram, the opposite angles are in fact congruent to each other. So we know now that if we have a parallelogram that has a right angle, that implies that all the other angles are right angles. And that is actually the definition of a rectangle. A quadrilateral is a rectangle if and only if it is a parallelogram with a right angle. And as we just saw, if it has one right angle, this means all the angles are right angles. But it is enough to show that just one is to prove you have a rectangle. So here we have our quadrilateral family tree, and branching off of parallelograms, we have rectangles. And once again, that's because a rectangle is a special kind of parallelogram. It is a parallelogram that has more special properties, like the fact that all of its angles are right angles. Here we're given that ABCD is a rectangle with diagonals BD and AC. We need to prove that BD and AC are congruent to each other. And we have a hint here. Our hint is which triangles have AC and BD as sides? Well, this triangle over here has AC as a side, and this triangle over here has BD as a side. Whenever I have overlapping triangles, a really good strategy is to take the two triangles and to draw them separately somewhere else on your paper so you can clearly see what belongs to each. Also, keep in mind that when you have overlapping triangles, there's going to be a shared component, something that's the same between both of the triangles, a side or an angle. And I see here from separating the triangles that AD is shared between the two triangles. It's the same two letters on this side and this side of the triangles. And if I look at the original diagram, that is where they overlap. It's in both green and yellow. I also know that ABCD is a rectangle. And a rectangle has all of the properties of a parallelogram and also some extra properties that make it super special. So one property of a rectangle that also is a property of a parallelogram that might be helpful here is the fact that opposite sides are congruent. So I'm going to fill that into our separated triangles as well. And since we do know this is a rectangle, we do know that all of the angles are right angles. So I know that angle A is a right angle, and I know that angle CDA, angle D, is a right angle. Here I can see that the two triangles BAD and CDA are going to be congruent by side angle side. And once I know they're congruent by side angle side, I can say that side BD and side CA, these corresponding sides, are also congruent due to CPCTC. So I'm just going to pause the video and write up the proof. You can feel free to write it up as well. Just make sure that everything that we spoke about in our plan, that we marked in our diagram, makes its way into your proof. So here we have the proof completely written up. And sorry that step number 7 is over here at the top. So you can take a second, pause the video, and read through the proof. We have just proven our second property of rectangles. So the first property was that all of the angles are congruent right angles. The second property special to rectangles is that the diagonals, so here the diagonals were BD and AC, that diagonals of a rectangle are congruent to each other. Here we're going to practice a proof using the properties of a rectangle that we just learned about. So we're given that quadrilateral mine is a rectangle. So if we know it's a rectangle, we know a lot of things about it. We know, first of all, that it has all the properties of parallelograms. So opposite sides and opposite angles are congruent. Opposite sides are parallel. Diagonals bisect each other. There's no diagonals here, though. This doesn't go all the way to the other end. This doesn't go all the way to the other end, so diagonals are not going to apply here. But we still know a lot of stuff. And since it's a rectangle, we do also know that all of the angles are right angles. So I'm going to fill in some of that information. So opposite sides are congruent. I do see triangles here, so I'm going to try to focus on the triangles because usually we're going to be proving triangles congruent to each other. The angles are right angles. And I see that the next given says that x is the midpoint of ME. Well, that's great, because if we know that x is a midpoint of the line segment, it splits the line segment equally into two congruent parts. And now we see that the triangles are congruent by side angle side. And now that we know triangle IMX and triangle NEX are congruent, we can say that the corresponding sides IX and NX are also congruent due to CPCTC. So pause the video and write up the proof. I'm going to do the same thing as well and try to make sure that everything that we marked in the diagram makes its way into the proof. Okay, here is the written up proof. So you can take a second, you can pause the video, and you can read through it, but notice that everything that we put in the diagram to prove the triangle's congruent is in the proof. And then finally, it ends with proving that the corresponding sides are congruent using CPCTC. Okay, so now we're going to talk about some coordinate geometry proofs with rectangles. So we already know that if a parallelogram has a right angle or it has congruent diagonals, then that means it's a rectangle. Those are our two special properties that make a parallelogram extra special, that make it a rectangle. So before we can prove that a quadrilateral is a rectangle, it first does need to be a parallelogram. So remember, parallelogram first and then rectangle. So if we wanted to prove that a quadrilateral with specific coordinates is a rectangle, we would need to do two things. First, we don't know the quadrilateral is a parallelogram. And remember, parallelogram first and then rectangle. So we would first have to prove that we do have a parallelogram. And then after we prove that we have a parallelogram, we can prove that the parallelogram is also a rectangle by proving one of the special properties of rectangles. So to prove it's a parallelogram, you can choose whichever properties specific to parallelograms that you want to prove. So you can either prove that opposite sides are congruent, that opposite sides are parallel. You can prove that the diagonals bisect each other, or you can prove that one pair of opposite sides is both congruent and parallel. Whichever one of those properties, just one. Write down your formula, show all your calculations, and then end with a concluding statement summarizing what your calculations showed. Then, once you prove it's a parallelogram, you can do the same thing to prove it's a rectangle. You can either show that there is a right angle. That would be with slope formula, showing that you have opposite reciprocal slopes, perpendicular lines that makes a right angle. Or you can show that the diagonals are congruent, and that's distance formula. Same process. Write down your formula, show your calculations, and write a concluding statement. So I'm just going to do one way for proving it's a parallelogram and proving it's a rectangle. There's multiple answers here. You can prove any property of parallelograms that you choose to, and any property of a rectangle that you choose to show that this is in fact a rectangle. So here's one way of answering the question. Once again, there's multiple ways that you could do it that would totally be correct. So I first showed that I had a parallelogram by finding the midpoints of the diagonals and showing that they are the same. So since the midpoints are the same, the diagonals bisect each other, making ABCD a parallelogram. And then to show it's also a rectangle, I found the length of the diagonals. And since the parallelogram has congruent diagonals, it means it's also a rectangle. So now we're going to talk a little bit about a quadrilateral called a rhombus. So by definition, a rhombus is a parallelogram that has congruent consecutive sides. So consecutive sides are any two sides that are right next to each other. So I will just say AB and BC are congruent because, once again, it is a rhombus, and rhombuses are parallelograms that have congruent consecutive sides. So since ABCD is a rhombus, it is also a parallelogram. So it has all the properties of parallelograms as well as special properties of rhombuses. Let's try to think about what we can conclude here from knowing that ABCD is a rhombus. Well, I know that if two consecutive sides are congruent, well, a rhombus is also a parallelogram. So opposite sides of a parallelogram are congruent. So that means AB and DC are congruent. And that means BC and AD are congruent. So guess what that means? That means all the sides are the same. So that means a rhombus is equilateral. All of its sides are the same length. Let's continue. Let's focus on, let's say, these two triangles over here for right now. So I see that these two triangles share side BE in common. And I see diagonals here, and I know that a property of parallelograms is that the diagonals bisect each other. So that also applies to a rhombus. That means this diagonal is being split equally in half. And also, I can put it in, maybe it'll be helpful later, this diagonal is also being split equally in half. Be careful, diagonals are not congruent. That's a property of a rectangle, not a rhombus, and rectangles are separate from rhombuses. They both start as parallelograms, but they are separate from each other. They're both special types of parallelograms, but they are separate from each other. Okay, so now I can see that these two triangles are congruent, and look, these two triangles at the bottom are congruent as well. Wow. So if I have a bunch of congruent triangles here, then I can use CPCTC to prove a lot of things. First, I'm going to say that this angle and this angle are congruent, and this angle and this angle are congruent, because they are corresponding angles in the congruent triangles. That's CPCTC. And in these two triangles and these two triangles, I can say the same thing. There we go. So not only do we have that opposite angles are congruent because a rhombus is a parallelogram, and that's a property of parallelograms, but we also just now see that if we have a rhombus, the diagonals actually split each of the angles equally in half. So the angles are actually getting bisected. So a special property of a rhombus is that the diagonals are angle bisectors. They cut the angles in half. And also, we can use CPCTC to say this angle and this angle are congruent, and this angle and this angle are congruent. But if these are congruent angles and they're also supplementary to each other, then they have no choice but to be 90 and 90 to make 180, 90 and 90 to make 180, 90 and 90 to make 180, 90 and 90 to make 180. So all of these angles here in the middle, where the diagonals meet each other, where the diagonals intersect, are actually right angles. And remember our special word for lines that meet to form right angles, that intersect to form right angles, we call them perpendicular. So we actually have just shown here that the diagonals of a rhombus are perpendicular to each other. So here we have our extra special properties of rhombuses that make them more special from just regular parallelograms. And that's that rhombuses are parallelograms with two congruent consecutive sides. And as we just saw, this implies that the rhombus is equilateral because it means all the sides are equal. We know that a rhombus, from what we just saw, has perpendicular diagonals, so diagonals that meet to form right angles. And we know that it also has diagonals that bisect its angles. We just saw that as well. Each of the four corner angles are bisected by the diagonals. So let's do one example together. We'll do a proof involving our special properties of rhombuses. So we're told here that BE bisects angle DBG. So that means angle DBG is being cut in half. We know that angle DBE is congruent to angle DEB. So if we already have a mark on angle DBE, that means I'm going to put the same mark on DEB because they're congruent. So we see that these are all congruent to each other. That's transitive property already. So we're connecting some things together. We're told that BD is parallel to GE, and we need to prove that DBGE is a rhombus. Well, they don't tell us that this quadrilateral is a parallelogram. And remember, parallelogram first and then rhombus. So we actually are going to have to first prove that we have a parallelogram here. Not so fun. But don't worry, it's not as hard as it looks because I see that these parallel lines are intersected by this transversal, and I see that we have those congruent alternate interior angles that are formed. But if you take a look, the two lines that we don't know are parallel are also intersected by a transversal, and we also have congruent alternate interior angles. And if our alternate interior angles are congruent, that was given to us that they are congruent, then that proves that the lines forming them are parallel. Congruent alternate interior angles make lines parallel. So now we know that we have a parallelogram because in our quadrilateral, both pairs of opposite sides are parallel, and that's one method of proving that we have a parallelogram. So now we're halfway done. The only other thing that we need to prove is that we have a rhombus. So we just need to prove one of our special properties of rhombuses. And guess what? It's already there for us. We know that in a rhombus, the diagonals are angle bisectors. And we see here that angle B is being bisected. So the diagonal is acting as an angle bisector here. And if we have a parallelogram whose diagonals bisect the angles, that means it is a rhombus. So I'm going to take a second and write the proof. You should do the same. Okay, here I have the complete written up proof. So you can take a second, you can pause the video, and you can read through. But notice how we proved that DBGE was first a parallelogram, because if both pairs of opposite sides are parallel, that makes the quadrilateral a parallelogram. And then we proved that DBGE was also a rhombus, because a parallelogram whose diagonals bisect the angles is a rhombus. The last thing we're going to talk about in this video is coordinate proofs to prove that you have a rhombus. So same thing as with a rectangle. Before a rhombus can be a rhombus, before a quadrilateral can be a rhombus, it first must be a parallelogram. So if the question just says the word quadrilateral, if it doesn't say parallelogram, then you don't know it's a parallelogram. You actually have to prove it first before you can prove that you have a rhombus. So just like with a rectangle, you're going to pick one property of a parallelogram to prove, to show that it's first a parallelogram. And then once you do that, you can pick one of the extra special properties of rhombuses. So we have either that two consecutive sides are congruent, that's distance formula, or you can show that the diagonals are perpendicular. That's showing that they make right angles where they intersect. So that's slope formula, showing that you have negative reciprocals for the slopes of the diagonals. You can't really show that the diagonals bisect the angles because it's hard to show about angles that are not right angles in coordinate geometry. So your two options are slope formula with the diagonals to show that they have negative reciprocals, or distance formula with two consecutive sides. The choice is yours. Once again, you should try it out. I'm going to pause the video and I'm going to show you one way to do it. I'm going to use a different property of parallelograms than I did before with the rectangles. With the rectangles, I did the midpoint formula of the diagonals to show that the diagonals bisect each other. I'll use a different property so you can see another one done for this one. Here is one way of doing it. To prove that it was a parallelogram, I used the distance formula and showed that the opposite sides were congruent. And since all of the sides ended up being the same length, the consecutive sides were congruent, which showed that the parallelogram was also a rhombus.